This is the comet Kohoutek, observed in 1973. Comets have interested astronomers for thousands of years, because of their spectacular appearance, and more recently because of the paths they take. Observations of paths of such heavenly bodies originally led Kepler and Newton to their ideas about orbits and about gravitation. Today we understand their theories in terms of scalar and vector fields. We're going to look at comets and other phenomena, all of which involve scalar and vector fields. But we're going to go a stage further than that. We're going to look at the way the scalar and vector fields are linked together. Let's kick off by looking at a comet. Here's another comet, a very famous comet. It's Halley's Comet. The white line shows the path it takes as it moves through the solar system. Now, the first thing you notice about this path is that it's not a straight line, and that's because the comet's moving in a force field. The force field's due to the gravitational effect of the Sun and the planets. Now, for all practical purposes, the comet is only affected by the Sun. That's because the Sun's more massive than the planets, much more massive. Right then, so it's the force field of the Sun we're going to be interested in. Let's see if we can't get a better understanding of this vector field.
Now I can demonstrate this vector field. The puck moves across the surface of the table virtually without friction. And I can put a force on the puck by connecting it up to this string coming from the centre, and the centre will represent the Sun for us. Just put it on, and now, under the influence of this force, if I send the puck off, I get an orbit. Let's look at that again, this time from above. So the force on the puck is having that effect on its motion. If I just let the puck go, then it falls in towards the centre, so it's in a force field towards the centre. I can find out more about the force. It's related to the distance out from the centre. So if I measure it with the ruler and then using the spring balance that has divisions on it, I can take a reading of the size of the force. So connecting it up like that, when it's out at this mark, when the centre of the puck is opposite that mark, then it balances with a force of 4. And then as I draw it out to twice the distance, the force that balances it now is 1. So the force has been divided by a factor of 4. That is, as the distance is doubled, the force reduces by a factor of 4, or a factor of 1 over 2 squared. And in fact, the force is proportional to 1 over the distance squared out from the centre. Now we can have a look at the graph of that. If you look at the graph, you'll see that for small distances, the force is very large, and as the distance increases, the force decreases. Well, bearing all that in mind, let's have a look at the orbit again. You can see that it follows the path of Halley's Comet, which means that the puck and the comet must be feeling exactly the same kind of force. The force field is proportional to 1 over the distance squared, and it's also towards the centre. We've got a magnitude, we've got a direction, and that gives us a vector field.
Anne's just shown the comet moves in a vector field, and even more, she's found just what the vector field is. Now then, I want to make what appears to be a digression. Although it seems that way, in fact you'll later see that it isn't. I want to pick up a point made in the last programme about a link between scalar and vector fields. To do that, we want a phenomenon which is an example of both a scalar and a vector field. This is a block of gelatin. We've put a blob of dye in the centre. Now when you do that, the dye doesn't stay put. It diffuses outwards. It's rather like when you drop a blob of ink on blotting paper and watch it soak out. Now, look closely at that. You'll see a darker patch in the centre where the dye is more concentrated, and then it'll fade out a bit towards the outside where the dye is expanded outwards. Now, in fact, we've got more than one of these, and we started them off at different times. This one was started about 2 days ago. The next one was started more recently, this one more recently still, and right down to this one, which was started only this morning. That means this one has been running for a comparatively short time, this one for a few hours longer, this one for a few hours longer than that, and so on to the end one, which has been running for 2 days. Now, I want to show you the first three in chronological order, one after another. I want you to see how the dye expands radially outwards. Now, that's obviously a vector field. Let's see why. Suppose I took one of these blocks, say this one, froze it at an instant in time, and then chopped it in half. We'd see something like this. A snapshot of the blob taken at an instant in time. The dark patch in the centre is where the dye is more concentrated, and you can see where it's diffused radially outwards. Now, let's look at a given point here. We've got a magnitude, the rate of diffusion. The rate of diffusion is just the rate at which the concentration spreads outwards. And we've got a direction, radially outwards. Not only that, but we can see a pretty obvious scalar field, the concentration. Concentration is just a scalar. It's high here where the blob's dense, and it's much lower here where the blob's more diffuse. In fact, we can see that the concentration depends in some way upon the distance from the centre. So in fact, I can put contours on this, contours of constant concentration. Now, what about this link between the scalar and vector fields? That's what we're really interested in. And we can see there must be a link because the dye is clearly moving from regions of high concentration towards regions of lower concentration. Now, the concentration's constant on one of these contours. It's also constant along this contour. So the change in concentration from one contour to another is the same whichever points on the contours we move between. If we look for the maximum rate of change of the concentration, that means taking the shortest distance between the two contours. So it's the maximum rate of change of concentration we're interested in. And that maximum rate of change is radially outwards, precisely the direction of our vector field.
You remember from the last programme that the vector field associated with a scalar field is just the directional derivative of maximum magnitude. That is, the derivative perpendicular to the contours. Now what I want to do is to work out an algebraic expression for this derivative of maximum magnitude. So let's see how it goes. First of all, I'll draw a contour line of some function, f of x, y, and it'll be equal to a constant along the contour, c1. Then another contour next to it will have the same function equal to a constant, but this time it'll be a different constant, say c2. Now, as I move from this contour onto this one, I'm going to get a change in f, but that change will be a maximum along the shortest distance. And when these contours are very close together, that shortest distance will be perpendicular to the contour here. Now, we want an algebraic expression for this directional derivative of maximum magnitude, and it's given a special name. It's called the gradient of the function, and it's written grad f. Now, it's a vector because it's got direction and magnitude. It's either pointing outwards or inwards. So I can write it as a vector but I don't know what to put for it, so at the moment I'll just put AI plus BJ. Well, the one thing that we do know about grad f at the moment is that it's perpendicular to this contour, that is, it's perpendicular to a tangent drawn at this point. Now, a vector along that tangent, say ds, I can break down into two parts. If that's ds, then I can break it down into dx in the x direction and dy in the y direction, so that I can now write that ds is equal to dxi plus dyj. Now, because the gradient of f and ds are perpendicular, if I take the dot product of these two vectors, I'll get 0. So that means that 0 is equal to a times dx plus b times dy. So far, so good. I can write another expression involving dx and dy, which will lead us to finding expressions for a and b. Along the contour, f doesn't actually change, but I can write that df is equal to df dx dx plus df dy dy. Now, along the contour then, df is going to be 0, so that means that given the same dx and dy here, it'll all fit together if I write df dx for A and df dy for B. That is, up here, I'm going to put in here df dx and df dy instead of B in that place. All right, so we now have an expression for the gradient of our function f. It's just grad f is df dxi plus df dyj. Now, that's all right for a function that's a variable that depends on x and y only, but in the unit you'll find it derived for a function of x, y and z, and that involves an extra term. And the extra term, you won't be surprised to see, turns out to be df dz k. So that gives us a more general form of the gradient of a function f. Well, let's try that out on an example. You've already worked out some partial derivatives for a function in the unit, and the particular function was f of x, y, z was equal to r, or in other words, the square root of x squared plus y squared plus z squared. Okay, so let's plug that in to the formula for grad of f. Grad of f then is df dx. Well, differentiating that with respect to x, you worked out beforehand, is x over r. So it's x over r I, then df dyj, df dy, you worked out to be y over r. So it's y over rj, and df dz is z over r k. Well, you'll notice that 1 over r is a factor in each of these terms. So I can put 1 over r as a factor, and that leaves xi plus yj plus zk, and that is our vector r. Well, you should recognise this as being a unit vector in the direction radially outwards. That gives us then the gradient of f for this particular function f. Now, I deliberately did that example because it enables me to go on now to work out the gradient of any function that solely depends on the magnitude of r. You remember Dan's diffusion experiment? He saw that the concentration depended on the distance out from the centre. That is, it was a function of the magnitude of r. Now let's work out the gradient of the concentration and see what we get. Well, I don't know exactly what the concentration is. All I know is that it's a function of r, so I'll write it as C of r, and then work out the gradient. So grad of C of r is equal to dc dx I plus dc dy j plus dc dz k. C is only a function of r, so I'm going to have to use the chain rule to work out what dc dx is. dc dx is equal to dc dr times dr dx. Oops, dr dx. And we've just worked out that dr dx is r over x. So this is dc dr times, it's x over r, sorry. Okay, so let's put that in. I can work out similar expressions for dc dy and dc dz. And it'll give me that grad of C of r is equal to dc dxi, that's dc dr times x over r I, plus dc dyj. Well, the similar expression is dc dr y over r j, plus dc dz, that's dc dr z over r k. Well, there's quite a few common factors knocking around there. First we've got dc dr, then we've got 1 over r, and if I take both those out, it'll leave me with xi plus yj plus zk, and that's our old friend r again. Taking this combination together, we've got the unit vector in the radial direction. Now, we don't know what dc dr is, but what this does show us is that the gradient of c is in the direction radially outwards from the centre.
We were looking for a link between a scalar field and a vector field, and we seem to have found it. We can get a vector field by going through that process of taking the grad of a scalar field. The gradient of a scalar field is a vector field. And we've seen that it works, as far as the direction's concerned, for our diffusion experiment. Now, we can't check the magnitude. It's too difficult to do that experiment here, so you'll just have to take our word for it, I'm afraid, that in fact that works all right. Back to the comet. Remember the state of play when we left the comet. We knew the comet was moving in a vector field, and we found out what that vector field actually is. Physically, though, there's no obvious scalar field, and that's a pity. It's a pity because if we did have a scalar field, scalars being easier to work with than vectors, we could work with the equivalent scalar field all the time. Now, it doesn't really matter that physically there isn't an obvious scalar field if we can get one mathematically. Can we perhaps find a scalar field whose gradient will give us the vector field we want?
Well, the first step in the hunt for the scalar field is to write down just what the force is. Now you remember that the force was proportional to 1 over the distance squared. We can write that as k over r squared. And it's in a direction in towards the centre, and the direction then is r over r, the unit vector in the radial direction, and it's inwards, that's in the negative r direction. So that's the force. Now, if we have got a scalar field, which I'll call S of r, and we take the gradient of it, then that's equal to ds dr times the unit vector in the radial direction. Well, by comparing these two, we want our vector field to be the gradient of the scalar field, so you can see that ds dr must be equal to minus k over r squared. And if we've differentiated something to get minus k over r squared, then the thing that we differentiated must have been k over r, plus a constant. So a scalar field that's proportional to 1 over the distance from the centre will provide the vector field that we need for the orbit.
Right, well I think we ought to try that out. So far we've only seen that taking the gradient of a scalar field gives the right direction for the vector field. We've not yet checked the magnitude. Now we have a rather nice way of doing this. Remember, Anne got a 1 over r form for the scalar field. Now we've taken that 1 over r curve, that's here, and we've rotated it about here to generate a surface. That means that an object on this surface at a distance r from the centre here is at a height 1 over r. And of course, if I release it, it will move. Now it so happens that the path it will take for this kind of a setup will be approximately the path it would take if moving in that scalar field. Except that you might have noticed this time the ball went the wrong way. That's because I need the surface inverting. Well, in fact, we have the surface inverted. You can see that if I take this, it fits exactly the surface we've got here. In fact, it's not very easy for me to take out. And also, I've been provided with a means of projecting a steel ball across the surface. Now, let's take a look at the way that works from above. You'll be able to see the path of the ball, but it goes very quickly, so you'll need to watch closely. I'll give you a countdown. 3, 2, 1, go. I'll do that again. 3, 2, 1, now. Now, we can see from that it has roughly the comet orbit. It looks like it. But we want a better comparison than that. We know with the puck we could get a comet orbit, so let's have another look at that. Now, we'll take that orbit we've got and we'll lay it over the top of this. At least this is much smaller than the table the puck was on, but we can lay the front part of it across here, and I'll try and fire this steel ball in such a way that it follows the orbit. 3, 2, 1. Well, that wasn't too bad, was it? So we've seen there can be a connection between scalar and vector fields, at least as far as the phenomena we've looked at are concerned. The gradient of the scalar field gives the vector field. Furthermore, we don't need an obvious physical scalar field. A mathematically constructed one will do the job just as well. It's easier to work with scalars than vectors, so we now have the option of working with an equivalent scalar field.